Hey guys, this is Mrs. Steele, and I wanted to give you guys the second half of this acid-base titration calculations worksheet. The whole purpose of this assignment is for you to be able to look at a titration curve, specifically this time for a weak acid, strong base titration curve, and be able to predict what the pH would be at any point along the curve. So this is what the title page of the assignment looks like. What I'm going to do now is just scroll on down until we get to example number 2. So flip in your note packet until you get to example number 2. And it starts out by stating that you have a titration with 25 milliliters of 0.100 molar acetic acid, and it's reacting with a strong base sodium hydroxide. So step 1, let's picture what this might look like throughout the entire titration. Begin with a y-axis, which will be pH. And you know that the pH scale goes from 0 all the way up to 14. And then on the y-axis, or excuse me, the x-axis, let's label that as the volume of the titrant that you're going to add during the titration. And specifically, our titrant that we're going to add in this titration would be sodium hydroxide. All right. Now, let's go ahead and think about what a titration curve for a weak acid and strong base would look like. Well, since we have a weak acid, we know it'll still be in the pH range of just any typical acid, but it maybe will be a little higher than a typical strong acid would be. It'll be maybe around pH of, let's say, 3, so maybe about here, okay? That's because not all of the acid is going to ionize in water. Okay, now I know I don't have that perfectly drawn to scale, but I think you guys can do a better job sketching than me. Excuse me. Now, I'm also going to label the volumes in intervals of 10 milliliters each on the x-axis, so 10, 20, 30, and 40. So let's just estimate or predict what we think would happen along this titration curve. And I'm going to change color so you guys can see it a little better. So how about maybe a purple? Boom. Okay. So I'm going to say we know that a weak acid will start with that dramatic fishtail, but then immediately start to enter into what's called the buffer region, maybe in around pH 4-ish or so. Then when I'm getting about at the equivalence point, you're going to see a dramatic spike in the pH. After all of the acid has been neutralized, then the titration will continue and will eventually plateau out at the pH of a strong base. And that will probably be in a pH range of, I'm going to say at least about 12, if not even perhaps just a little bit higher, like that. Okay. So what are some things that we could identify about this graph? Well, for sure, this is a weak acid, strong base titration. We're not using hydrochloric acid this time. Rather, we're using acetic acid. And we're reacting it with sodium hydroxide. So weak acid, strong base. At the equivalence point, which I'll mark with a pink marker, notice that that would be the halfway point between when the pH first jumps up and when the pH starts to stabilize after the equivalence point. So probably about here might be good. Okay, about there. And also notice if you kind of eyeball over that this is a little bit above pH 7, and that would make sense because at the equivalence point, you're going to have a little conjugate base that makes the pH a little higher than 7. All right. So the equivalence point will be at a pH greater than 7. All right, next. What are some things that we can do with this graph? Well, we can determine the molarity of the sodium hydroxide pretty fast. Given the acid information, which was located at the top, as well as the volume of the base, which was at the equivalence point. And that was about 25 milliliters of base to get us to the equivalence point. I could also calculate the pH at 4 different locations along this titration curve, perhaps initially here, I could calculate the pH. Let's see, where else? In the buffer region, right around here. I could also calculate the pH at the equivalence point, as well as somewhere beyond the equivalence point. So those are the 4 locations in which I could determine the pH. Okay, so those are what we're looking to learn how to do today. Some other quick things that you can do just based off the equivalence point is calculate the moles of acid that were required or that were consumed in order to neutralize all that acid. And also how many moles of sodium hydroxide must have reacted with that acid. Now, a quick little fix on our presentation here. Remember, we're doing a weak acid titration, so scratch out that HCl. Let's put acetic acid. All right, we're ready to rock and roll. So some quick calculations. For example, what is the volume of the base at the equivalence point? So look at your graph and go back to where we marked it with an X. And then look down at the x-axis, and I see that it's at 25 milliliters. So write that down. Also consider what's the balanced equation for this reaction. We're taking a weak acid, reacting it with a strong base. That's an H. And we're producing sodium acetate, which is insoluble salt, and water, which is a liquid. So simplify this down to the net ionic equation. When I write the net ionic equation, I need to eliminate any spectator ions, any weak spectator ions. So I notice the sodium ion here, which comes from a strong base, that's going to remain a spectator ion throughout the reaction. So I'm going to eliminate that when I write my net ionic equation. However, the weak acid does not dissociate or ionize very well, so you need to leave that intact as just one whole molecule. So we've got acetic acid reacting with hydroxide ion, and it's going to produce conjugate base, specifically the acetate ion, and our other product will be water in the liquid phase. All right. If you remember to try to include the states of matter, that would be appropriate. If you need to as well, make sure you label these to help you keep track. We've got the weak acid as a whole molecule. We have that strong hydroxide ion from the base. Then we have our conjugate base right here. And then we have, I guess you could say, your conjugate acid water as well. Some final things that you can do with this information. You could calculate the molarity of the base, number 3 from our notes up here. So I'm just going to do that in this little scratch space since I have this handy. You know that the molarity of the base times the volume of the base is equal to the molarity of the acid and the volume of the acid. Just to be careful and to consider coefficients, I'm going to put the B for coefficient for the base in the balanced equation and the A right there for the coefficient for the acid in the balanced equation. But we luck out in this particular case because the coefficients in front of the acid and base are 1 and 1. So what we put here and here will be 1 and 1. So I'm just going to rearrange this and I'm going to solve for molarity of base. So if I do that, the molarity of base is equal to 1, that's the coefficient of the base, that's B, times the molarity of the acid, which is 0.100 molar, times the volume of the acid, which is 25.00 milliliters, divided by 1, which is the coefficient in front of the acid, and then times 25.00 milliliters, which is the volume of the base, which we used at the equivalence point. Do the math here, and I think you'll notice the volume and the coefficients there for the acid and base cancel. So the only thing you're left with is 0.100 molar, and that's our solution. That's our molarity of our sodium hydroxide. Okay, so there we go. So we have figured out the molarity of our sodium hydroxide, even without having to do any other calculations. Now, for the remaining part of this video, I'm going to go through each one of the types of pH calculations that you might see. To be perfectly honest, they don't have time on the AP exam to ask you to do every single one of these, but you need to be prepared to handle whatever they toss out at you. So let's take a look at phase 1. This would be before the titration has actually begun. In other words, we're going to use the initial information about the acid that we had at the get-go. At the beginning of the reaction, or before we even do the titration, the only thing that you have in your Erlenmeyer flask is acetic acid. Okay, so remember the Erlenmeyer flask is down at the bottom of our titration apparatus. So that would be the only thing that's in here at the beginning. Now, of course, arguably, you guys know we might use a pH meter or an indicator such as phenolphthalein in order to tell when we're at the end point. But for practical purposes of what we're talking about right now, our focal point is on the weak acid. So if we could get down to the particle level, what would be the dominant species that are present? Well, a weak acid by definition does not ionize or dissociate very well into hydrogen ions. It only releases a minimum amount of hydrogen ions when it interacts with water. So I'm going to have to use these little reversible reaction arrows here to indicate that this reaction is at equilibrium. And I'm going to write that a little bit of hydronium is produced as well as my conjugate base, which is acetate ion. Okay? Those are both aqueous for those of you that are tracking our states of matter. Now, some textbooks and some websites may write it more simply without showing the water molecule. So they may just say acetic acid can dissociate just a little bit to produce hydronium ions and hydrogen ions and conjugate base. So this is another way that the same reaction could be written, and it would be perfectly acceptable. So what would you show in a particle drawing at this point in the reaction? I recommend that you draw multiple weak acid molecules. So I'm going to draw at least 3 or 4. Excuse me. But maybe I might also draw one little hydronium ion, H3O+, and maybe one conjugate base, just so that I remember that a little bit of this is going to form those. So notice how we have just a little bit of ionization taking place here. Okay. We're talking like maybe 1%, definitely less than 5% of the time. You're going to see a lot of weak acid, and you're not going to see very much hydronium ion because it's a weak acid. So what are we going to do? Well, guess what? At this point in the semester, you have already learned that Ka is a fundamental quantity that you need to know regarding weak acids. Ka, by definition, is the acid dissociation constant, and we would use this expression anytime we have a weak acid that is dissolving in water. Okay? So you also, besides a Ka value, you also need to consider using an ice table to organize your thoughts and help you determine the molarity of all of your chemical species at equilibrium. So let's go to a reference table. You could find the one in the back of your textbook, or you could even just do an internet search for what's the Ka of acetic acid. And when you do, you'll find that that answer is 1.8 times 10 to the negative 5. You will be given this on an assessment, so don't stress about trying to memorize that. Next, I recommend you do a rice table. So you write out the reaction again, just so you have it right there in front of you. And we know we make a little bit of hydronium, and we make some conjugate base. Now, if we go way back, you may have forgotten, but if you go back a page, you'll see that we knew the molarity of the weak acid from the get-go. So that would be our initial concentration of our weak acid before the reaction has taken place. So it was 0.100 molar. The concentration of the water is irrelevant because it's in such high amount. So we're just going to mark that out for our K expression. Also, it's a liquid in this reaction. It's a pure substance that's in the liquid phase. So we're going to also ignore it as part of the K expression. And then hydronium and acetate, which is our conjugate base, we assume we have nothing to begin with. All right, let's go to our change. Well, you can already see that our reaction has to proceed in the forward direction because we don't have any product yet. So in order to be at equilibrium, you have to have a little bit of each of the chemical species at the end of the reaction. So we have to proceed in the forward direction to produce some of that product. So at equilibrium, I have lost X amount of my original acid, and I have formed X amount of hydronium and acetate. All right, what do we do now? Well, I can write me a Ka expression. Ka equals the hydronium concentration times the conjugate base, acetate. So that's products. And then over our aqueous reactants, which is the acetic acid. And then I look at my equilibrium, this part of the rice table, and I see, oh, I know X is hydronium concentration, and I know I have the same concentration of conjugate base. And I'm going to divide that by the molarity of the acetic acid at equilibrium, which is 0.100 minus X. This is all equal to 1.8 times 10 to the negative 5, which we looked up in our reference table, right? Well, put this little note on your paper, and you've heard me say this time and time again. We can use the 5% rule since this Ka value is quite lower than 1. We can assume that X is way less than that initial concentration of acid. Okay. Okay. So that actually helps us eliminate the X in the bottom part of the reaction. So if I rewrite this again, I would say 1.8 times 10 to the negative 5 is equal to X squared over 0.100. And then I know y'all can rearrange this, so I'm going to skip a few steps. Make sure you do the 0.1 times the 1.8 times 10 to the negative 5, and then take the square root of that, okay? So X equals 0.0013 molar. At this point, sometimes students lose track of what they've been doing. So go back to your rice table to remind you that X is the concentration of hydronium and conjugate base at the equilibrium. That is your concentration of hydronium ion. And maybe not as important, but still true, it is the concentration of your conjugate base. Well, why do I need the concentration of hydronium ion? Go back to what the question is. We're trying to figure out the pH before the titration begins. So I'm going to take my concentration of hydronium ion and plug it into the pH equation. And I find out that it's 2.87. Pause. Does this make sense? Well, if you think about what's happening, initially, we have a weak acid. So we're here. And it would make sense that our pH is in the acid range, but maybe not quite as low as if it were a strong acid. So this is quite acceptable because we have a weak acid, which will have a higher pH normally than a similar molarity strong acid. So notice how I'm putting a little caveat on here, assuming that you have a strong acid with the same or a very similar molarity. Very good. So that is phase 1. Let's go to phase 2. What could the pH be if some of the base is added, perhaps 12.5 milliliters of base, but we're clearly before the equivalence point, because the equivalence point is when you have 25 milliliters of base. Okay. Well, if you think about where we are on our graph, we're in that flat region. So let's back up a little bit. We are here. That's called the buffer region. Okay. We're in an area on the curve where the weak acid and the conjugate base of that weak acid are resisting changes to pH. So notice that the pH is staying kind of steady in this point in the titration curve. Well, what's going on at the particle level? Well, we're going to have less acetic acid than what we started with because some of that reacted with the hydroxide. So I'm going to draw maybe 2 molecules of acetic acid. The sodium ions are starting to accumulate. Those came from the strong base that I put in the solution. And notice that it's in equal proportion to the amount of acid that I lost. So I gained 2 sodium ions because I had the hydroxide ions react with the weak acid. And so I lost 2 moles of weak acid, and I have gained 2 sodium ions. I also have some conjugate base that has formed during this reaction. So let's show those in our particle drawing. Some of that and some of that. And notice that that is in equal proportion to the sodium ions because they, as that weak acid is reacting, it's going to release conjugate base. So if I consume 2 moles of acid, I produce 2 moles of sodium ions, and I also produce 2 moles of of acetate, which is our conjugate base. You do not see hydroxide in the solution because it has reacted already with the weak acid. So it is not visible because it has already reacted and formed water with the acid. Okay, so what can we do at this point? One really quick calculation that you can do is calculate the moles of acid. And you can just use the molarity and volume of the acid, which has been known since the get-go. If you look back at the original question, it was up here. Okay. So I can use MAVA. Just take the molarity of the acid and multiply times the volume of the acid. Make sure it's in liters. And I find out that I've got 0.0025 moles of acid. Okay. And that's moles per liter there. So you can see the moles, the liters cancel, and we're left with moles. Another thing that you can do to kind of help you keep track is consider, well, what's going on with the base? We know the molarity of the base. We determined that way early on. So that was like right about here. A couple pages back. You know the molarity of the base. You also know the volume of the base. It explicitly told you, like just a little while ago, that you added 12.5 milliliters of sodium hydroxide. So just take that molarity and that volume and you get 0.00125 moles of base. Which one of those is going to be our limiting reactant? Maybe the base? I have fewer moles of base, that's for sure. Well, let's do a rice table, or you can call it a BCA table, before, change, after, if that makes you feel more comfortable. Oh, 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 oh. Pushed the wrong button there. Okay. So I've got acetic acid reacting with, what part of the base? Oh yeah, the hydroxide. Think about my net ionic equation. Okay. And I'm going to produce water for sure. And I'm also going to produce conjugate base. So I started with this many moles of acetic acid, and I know that I'm reacting it with this much base. Notice how I put moles in my ice table or in my BCA table. That was deliberate because I'm not working with molarity right now. Okay. All right, so let's keep going. So let's think. We just said that the base is our limiting reactant because we have fewer moles of it. So it's safe to say that all of that gets used up. And I have an equal amount of acid that gets used up. So when I do the math, I have no hydroxide left, but I do have 0.00125 moles of acetic acid left. Now, a side note for those of you that are like, well, where's the product side in this? Well, we know water is not part of our, like a focal point in our reaction. It's already in large quantity. It's a pure substance. We're making more of it, but it's not that significant for like keeping track of what the molarity is. Over on the other side, we have conjugate base, or acetate ion, which we had none of if you look at your particle drawing, but now we're producing some that wasn't there in phase 1. So we're going to see a gain of acetate ion in our solution. So here you go. You're going to have that many moles of acetate when it's all said and done. So what are you going to do with all this information? Well, the goal here is let's figure out what's dictating the pH right now. And if I had to choose between my weak acid and hydroxide, well, the hydroxide's all gone, so I guess the weak acid is what's dictating the pH right now. So I guess I need to get my concentration of my weak acid. So let's do that. Okay. All right. Remember, volumes are additive. You may want to highlight that if you have a highlighter. And I'm going to take my concentration of acetic acid by taking this, the number of moles that are left over once the sodium hydroxide has reacted. So these are the leftover moles of acid. And then dividing it by the volume, total volume of solution, which is the 0.025 liters of acid that we've had since the get-go, plus the additional 0.0125 liters that came from the base that came through the burette. Okay. Now, if you do that math, you end up getting 0.0333 molar. So that's your concentration of your weak acid. Why does this matter? Well, we've got to get the Ka for this and see if our pH that we calculate makes sense. This is a weak acid, right? So this is the molarity of the weak acid, but that's not the hydrogen concentration. Let's write a Ka expression for this. Ka equals, like what's actually going to happen here? We've got acid that can dissociate or interact with the water molecules to produce hydronium and some amount of conjugate base. And then you have this initial concentration of acetic acid, like that. So we're going to solve for hydronium ion. I'm going to rewrite this because if you're like me, I like to be able to see it. So I'm going to solve for hydronium ion. And if I do that, I end up getting Ka times HC2H3O2 divided by C2H3O2 minus, like that. What's going on at this point? Well, if you look really carefully, did you notice that our moles of our conjugate base and our moles of our acetic acid are the same? So since they're the same, in this particular instance, they're like exactly equal, then my hydronium concentration is equal to my Ka. What an interesting little shortcut there. If you don't believe me, go ahead and substitute in the concentration of 0.0333 and you'll notice it cancels out for both of those chemicals. So the hydrogen or hydronium concentration is 1.8 times 10 to the negative 5. So I guess you know what we're going to do next. We're going to calculate the pH. So the pH, which, side note, is equal to the pKa, is equal to the negative log of the hydronium concentration. I can estimate this pH without even trying. It's going to be about 5, but a little lower than 5. And if you put this in your calculator, you get a pH of 4.74. Is this reasonable for a weak acid titration? I hope the answer is yes for you. Go back and look. Our initial pH, whoa, okay, hold on, let me give my computer time to adjust here. Okay, my initial pH was 2.87, and now it has crept up a little bit, and it's at 4. What did we say? 4.74. Okay. So it is still in the acid range because we have leftover weak acid that hasn't reacted, but it's clearly higher than what we started with. So that's reasonable because some of the weak acid has reacted. Now here's a super important shortcut. Let me get my highlighter out and mark that for y'all. Wow! This is a shortcut and we need to embrace it. Okay. Did you notice that the volume of the base was 12.5 milliliters? So this is half the volume that's needed to neutralize all the acid at the equivalence point. We call this the half equivalence point. I'm going to do a really simple sketch of where we are on the graph. So remember, curves up, kind of fishtail, and then whoop, whoop. We are right here. Volume-wise, that is exactly half the volume needed before we neutralize the entire acid. So this is the half equivalence point right here. Okay. Why is this point special? Well, at this point, your acetic acid, your weak acid that you started with, is equal to its conjugate base that has been forming as the sodium hydroxide reacts with the weak acid. You have a buffer. Okay, so let's talk about the Ka for this. You know that when you write a Ka expression, you do products over the reactants. But if these are equal to each other, then I think we can just simplify that and say that the Ka equals the hydronium concentration. Woohoo! So please make a note of that. When you're at the half equivalence point, the Ka is your hydronium concentration. So if you get the pKa, and you know how to do that, just take the negative log of that, that's going to equal the pH. Wow! Shortcuts, and that took way less math. Okay? Excellent. Final note on this, You could use an ice table to figure out your moles of weak acid and your strong conjugate base that you've produced. Or when I say strong conjugate base, maybe I should say stronger perhaps than a spectator ions base type thing. So be careful with your wording there. You could use an ice table if you want to. Another option is you could use what's called the Henderson-Hasselbalch equation, and you can prove that the pH is correct. Okay? So the Henderson-Hasselbalch equation, and you can find this on your AP equation sheet, so please find it now. It states that the pH is equal to the pKa plus the log of the, and if we're talking about a weak acid strong base titration, it's plus the log of the conjugate base over the original weak acid. Okay. So if you're in a bind and maybe you're anywhere in the buffer region, it would be great to pull this up. So for any problems where you're in the buffer region, you can always pull this equation out to help you out. So if you know the Ka value, you can use that to get you to the pKa. So that's a negative log. Okay, negative log 1.8 times 10 to the negative 5. And then if you know the concentration of your conjugate base, even if it's not equal to your weak acid, so I just want to emphasize that it doesn't have to be equal to your conjugate acid. Just make sure you're in the buffer region, that helps. Over the concentration of your weak acid, you can take the log of that, and when you combine both parts of that equation together, you can get the pH. It just so happens that in this particular problem, the negative log of 1.8 times 10 to the negative 5 is 4.74. And if you take the log of 1, the log of 1, because you know this simplifies to 1 right here. So if you take the log of 1 right there, if you take the log of 1, you just get 0. And if you don't believe me, put log 1 in your calculator and you'll see. So 4.74 plus 0 is, surprise, 4.74. And that is the pH. So once again, I'm just telling you that you can use the Henderson-Hasselbalch equation, which is on your AP equation sheet, and that can help you predict the pH anywhere within the buffer region, even if the concentration of the conjugate base is not equal to the weak acid at that point. Let's pause and talk about some situations that might occur for AP questions. You might be asked, well, what if you have 5 milliliters of strong acid that are added to a buffer that's already prepared? What will happen to the pH? How will the pH change? So remember, at the half equivalence point, the concentration of acetic acid is equal to the concentration of conjugate base. So the pKa is equal to the pH, which is equal to 4.74. That's a 7. If we add HCl, then the HCl, which will completely dissociate to produce hydronium as soon as it hits the water and chloride ions, the hydronium will immediately react with the conjugate base that's floating around in the buffer. And when it immediately reacts, it will proceed to make water and acetic acid, which is the weak acid. Isn't that interesting? When you're in the buffer region, if you add an acid to a buffer, it reacts with the conjugate base and it makes more weak acid. Well, what's that going to do to your pH? You just added more acid to your solution, So that's going to cause the pH to go down at least a little bit. So that's one common question that's asked. Assuming you understand the role of a buffer, you need to consider, well, which solution is doing the motion there, okay? And then predict which way, you can predict which way the pH will shift. So if you're going to add some acid, the pH is going to go down a little bit, but it's still in the buffer region, so it's not a dramatic drop, it's just a small drop. Look at example 2 here. Here's another example of a type of question you might see. They might say, well, what if you add some strong base to your buffer solution? Well, think about what's going on. Once again, if you're at the half equivalence point, then the concentration of your weak acid is equal to your concentration of your conjugate base. Therefore, the pKa is equal to the pH at the half equivalence point, and that's 4.74. If you add sodium hydroxide, excuse me, the sodium hydroxide, you know, is a strong base. It will immediately dissociate, since it's already ionic. It will immediately dissociate to produce hydroxide ions. As soon as those hydroxide ions come in contact with the weak acid in the buffer, they will react, and I mean react completely. And they will produce some water, but more notably, I'm producing some conjugate base. So what will the pH do if I have some conjugate base? Well, it's going to cause the pH to go up or become a little less acidic and just a smidge more alkaline, but it's still in the acid range. If you don't believe what I'm doing here with the math, also consider using Henderson-Hasselbalch equation. Remember, pH equals pKa plus the log of the conjugate ion, which in this case is the conjugate base, over the original weak solution, which was in this case the weak acid. And if you're thinking about what's going on here, we're increasing in the conjugate base, and we're going down in acetic acid. So that causes the log that you plug in to be greater than 1. And when you do that, you should get a number that is larger than 0 if you take the log of that. So you'll actually get a value that's positive. So pKa plus some positive number, and you'll get a slightly larger pH overall. So there you go. So I just wanted to throw that out there because those are two common questions that are asked. Okay. All right, let's move on along. So at this point, we've made it past what I would call the most challenging part of this, which is phase 2. I highly recommend that you do some more practice problems in that buffer region, which is phase 2. Some of this other stuff that we're about to do is not so bad, but let's go ahead and dive on into the last part of our video. So for phase 3, we are now at the equivalence point. Yay! So this is once again where your moles of titrant have reacted completely, or they have neutralized your moles of your analyte. In other words, your moles of your base have completely neutralized your acetic acid, specifically the hydrogen part of that weak acid. So here's a hypothetical, keeping on with our big narrative here. Now we've added 25 milliliters of sodium hydroxide, and we have to consider what the pH will be. So we need to consider what species are present at the particle level. We know that all of the weak acid has been consumed. It's been reacted with hydroxide. So you don't see either one of those ions at this point. You do see spectator sodium ion, so I'll go ahead and draw those in. And you'll see 4 moles of them, I mean, based on our drawing here, which is the same as the moles of acid that you began with. You'll also see a strong, and I'll say ish, a strong, somewhat strong, not strong like literally a strong base, but a strong, relatively strong conjugate base. And you'll have equal moles of that. as you do as your sodium ion. So we've got 4 moles of that. Yay. That's it. So I have a salt. There's also water in the background that we don't draw because it'd be too tedious to include. So just be aware there is water because it's an aqueous solution. So what's the net ionic equation? What's going on right now? Well, sodium, you know, is a weak spectator ion, so I'm going to ignore that ion. It's not going to do anything. But that strong-ish conjugate base could possibly react with the water that's in solution. And perhaps we could produce a little bit of weak acid. Not so important right now. But more importantly, I'm going to have some hydroxide ion that I've produced. So that's where I really want to focus, is right here. So what do you think that's going to do to my pH? Well, I've got a strong-ish conjugate base, and that's going to cause my pH to be greater than 7. But the question is, how much greater than 7? So that's what we're going to figure out right now. So we're going to make us a rice table. Keep in mind that our reaction is conjugate base plus water making the original weak acid plus hydroxide ion. Okay. At the equivalence point, your moles of weak acid are equal to the moles of hydroxide, but they've been neutralized, so we don't see them. We don't see them in our particle drawing, but they were in equal amounts when they reacted. And then we have moles of conjugate base, and now that conjugate base is becoming a major focal point in predicting the pH. So what kinds of calculations can we do? Well, I can figure out the moles of conjugate base that I'll have at the equivalence point. I know the molarity of the base, and I also know the molarity of the original acid, and I know the volume of base that I added to the solution, which was 25 milliliters or 0.025 liters. Therefore, I have 0.0025 moles of conjugate base. So let's make a rice table. Let's have rice. Okay. R-I-C-E. Write your reaction out. I started with 0.0025 moles of conjugate base. We don't really care about the water, so mark that out. And we're going to assume we haven't yet let that salt make any weak acid or strong hydroxide right there. I know I'm going to lose X amount of that, and I'm going to gain X amount of my products, because that's kind of how the reaction is going to proceed. And then we have 0.025 minus X at the end of this phase, and I have X amount of my products. So what you're going to do, oh, wait, y'all want to do a Ka, but should I? Nope, I should do a Kb expression because I made hydroxide. So I'm going to write a Kb expression, but it still works the same way. You write products over reactants. So I just want y'all to pay attention to that. I wrote a Kb expression because I am definitely in the base range pH-wise. And my reactant that was really the game changer in this case was a conjugate base. So it'd be appropriate to write a Kb expression for how it interacts with water. So I wrote my Kb expression, and then I can just say x squared over 0.0025. Keep in mind that's moles, so I need to make it a volume. So the total volume that I have, if I had 25 milliliters of acid reacting with 25 milliliters of base, that'd be 50 milliliters total. So that's my molarity. Keep in mind that's a molarity. So that minus X. All right. A little tedious, but you can do it. Now you can write that little assumption like we always do. Assume X is way less than the original molarity, whatever we have right there. Okay, excuse me, sorry, the original molarity, 0.1 molar. So if I rewrite this one more time, then I would say X squared over let's see, 0.050. So I eliminated the X in the denominator. One other side note, since this is a KB and I don't currently have it, I have to do that little rearranged equation using KW. So KW divided by the KA is the KB. And I'm going to do 1 times 10 to the negative 14 divided by the Ka, which is 1.8 times 10 to the negative 5. And I get an answer of 5.5 times 10 to the negative 10. So that is the Kb for the acetate ion there. So 5.5 times 10 to the negative 10. And then you've got the X squared over 0.05. Y'all know how to rearrange the equation, solve for X. I'm going to skip that step because I feel like y'all are comfortable with that. So X is equal to 5.24 times 10 to the negative 6. And this is where you're like exhausted from doing all this math. But if you go back and remember, X is the hydroxide concentration at the end of this step. So since that is your hydroxide concentration, what can you calculate? How about pOH? Put that in your calculator. You get 5.280. Are we done? No. The question is not what the pOH is. Nobody really cares about that. We care about what the pH value is. So you have to take 14 minus pOH. So 14 minus 5.280, and you get a difference of 8.720. Pause. Does this match our equivalence point on the graph? You go back and look at your graph. And I hope that you notice, yes, it does. The conjugate base is going to react with the water, and it's going to release some hydroxide ion. And since we have some hydroxide in solution, and there's no H plus at this current moment, or not a substantial enough amount to matter, since we have an increase of hydroxide, our pH is going to be higher, okay? So just keep that in mind. Right, our pH is going to be higher. Another thing that I want you to note is at this point you've added so much. You've added so much base that your buffer is no longer able to resist the pH change, and that's why you see it shoot straight up, you know, as we're at the equivalence point. Okay? One more to go. I know you guys are hanging with me and being very patient. Let's go to phase 4 after the equivalence point. All right, so let's see what we've got here. We have already neutralized all our acid, but we're still adding more base. So what's there left to do? What could the pH do? Well, I already know that the volume of my base at my equivalence point is 25 milliliters, but I'm at 35 milliliters of sodium hydroxide, so I'm way beyond the equivalence point. What would be going on at the particulate level? Well, let's figure out what our dominant species are. So let's consider what has happened at this point. All the weak acid is gone. It has been neutralized. The sodium ions are going to continue to collect because you're dumping more sodium hydroxide in, and sodium ions are just spectator ions. So it's fine. Okay. Acetate ions are fixed at this point. They have not changed in amount. And that's because those acetate ions came from our weak acid. But since we have no more weak acid to react, we are at a constant concentration of conjugate base. There's just a fixed amount. 1, 2, 3. I think we need one more. Boom. Okay. Now, let's talk about hydroxide ions. This whole time, the hydroxide ion has been reacting with the weak acid. So you haven't seen it in any of the previous particle drawings. But now we're at the point where the hydroxide no longer has any weak acid to react with it. So it's going to start to collect. So there's a hydroxide, and oh, look, there's one more that's starting to build up because we have extra base that's dropping in. What's going to go on with the pH, or how are we going to figure out the pH for this solution? Well, I need to figure out which solution is really impacting the pH. And spoiler alert, it's the sodium hydroxide. The sodium hydroxide is a strong base. So when you put sodium hydroxide in water, it will immediately dissociate into sodium ions and hydroxide ions. So this is actually not really any different from if you got the pH for a strong acid at the beginning, except we need to think of it more as on the hydroxide end. So what are we going to calculate? We need to calculate the excess moles of hydroxide that are unreacted and they're beyond the equivalence point. Okay? That's our focal point. Whew, almost home, y'all. Hang in there. So we have a given volume of acid, 0.1 molar hydrochloric acid, and we're asked to calculate the pH if we have 35 milliliters of sodium hydroxide that have been added. So like we said on the previous page, you need to determine the excess moles of hydroxide beyond the equivalence point. 35 milliliters is the same as saying 0.035 liters, and that's your base. But how much actually reacted with the acid? If you remember, we were at the equivalence point when we had added 25 milliliters of sodium hydroxide. Okay? So if I subtract in liters, then I'm going to get 0.010 liters of sodium hydroxide that are in excess. Okay? Keep in mind that volumes are additive when we do our molarity calculation. So what we did was we were trying to figure out how much excess sodium hydroxide we've got. Let's look at this using moles. Okay, so let's move down here a little bit. We've got 0.010 liters of extra base, and we know the molarity of the base, 0.1 molar. So I have 0.0010 moles of extra sodium hydroxide. Okay. So just to be clear, since it's a 1-to-1 ratio of sodium hydroxide to hydroxide ion, I have 0.001 moles of hydroxide in excess. Okay. So how do we figure out the hydroxide concentration? I take my moles of hydroxide ion that are in excess, and I'm going to divide by, think volumes are additive, the total volume of solution. So let's go back and think about it. I had 25 milliliters or 0.025 liters of acid, and then I've dumped in 35 milliliters, which is the same as 0.035 liters. So that's a total of 0.060 liters if you're tracking that. Do that in your calculator, save yourself some pain and suffering, and do 0.0167. That's your molarity of your hydroxide ion. If you can get to this point, you can just slide on home. What can we calculate once we have the hydroxide concentration? That's right, the pOH. So the pOH is just the negative log of the hydroxide concentration. And then we get the answer of 1.778. You may be tempted to stop here, but why does that not make sense? If I'm looking at a titration curve and I'm at the end of a weak acid strong base titration, I should have a really high pH. So what do I need to do? Oh yeah, that's right. Take pH or solve for pH by taking 14 minus POH. There we go. That's the missing step. So 14 minus 1.778, and you get a final answer of 12.222 for the win. Does this make sense? I sure hope it does to you. Yes, our hydroxide concentration has increased, so the pH has increased too. And since there's no acid remaining in our solution, we notice that the pH skyrockets up to a strong base pH range. Well, I appreciate your patience as we have worked through all of these calculations. Please feel free to review this video at any time and ask me questions during class as needed.